Hello, everyone, and welcome to the latest episode of Scrubbing the Skies, the webinar series of the Institute for Carbon Removal Law and Policy at American University. I'm Wil Burns, and I'm one of the founding co-directors of the Institute. In recent years, there's been extensive discussion of the potential role of biomass in the realm of carbon dioxide removal, including afforestation and reforestation initiatives, bioenergy with carbon capture and storage, and biochar. Today, we focus on another potential approach, wood harvesting and storage. And to help us assess this are three experts in this nascent field. Ning Zheng, who's a professor in the Department of Atmospheric and Oceanic Science and the Earth Systems Science Interdisciplinary Center at the University of Maryland. Dan Sanchez, Chief Scientist for Biomass Carbon Removal and Storage with Carbon Direct, and Marian Tikkanen, Head of Carbon Removal Supply at Puro Earth. We will begin with a presentation by Professor Zheng and then move to some moderated questions and finally audience questions. So feel free to populate the Q&A box as we proceed. And so now we'll turn the floor over to Professor Zheng.
Do you see my screen now, Will? Do you see my screen?
Yes.
Great. Great. Thank you for the host, and thank you for the audience for being here today. And it's a great pleasure to discuss this somewhat novel idea called wood harvesting and storage via Wood Vault. Let me give a quick summary of the main points I want to make. What is wood harvesting and storage? Collect sustainably sourced unmerchantable residual woody biomass, stored in specially engineered structure called Wood Vault for secure carbon dioxide removal. The durability has been shown to be 1,000+ years if it's done right. And the cost when it's fully implemented at scale could be $10 to $50 per ton CO2 with very low capital investment. The carbon efficiency is less than 2% CO2 emissions if the transportation distance is not too far. And the method is distributed and highly scalable. And we believe it's ready to deploy at megaton scale in the coming years and possibly reaching gigaton scale in the 2030s. So a little bit history of WHS. The initial concept was proposed in 2008, and that was followed by, a DOE-supported workshop and the scientific consortium's work looking at the global harvesting potential and other relevant aspects. Then 2 demo projects were conducted. First, the Gemstone team project for 3 years in Maryland, Eastern Shore, that demonstrated the feasibility of WHS and developed the first methodology. And then from 2013, the Montreal project buried 35 tons of unwanted wood in an anaerobic condition. And this project collected valuable real-world operational data as well as understanding of the cost and durability. I will show a couple of slides shortly on this project. Then the carbon lockdown project was created to help to carry out WHS in the real world at real world scale. And there are ongoing research and projects going, as well as the need for team building. So if anybody's interested in collaboration, please feel free to contact me. And there are several other organizations that are also working on both research and in particular implementation. For example, the Yale Carbon Containment Lab, Inter-Earth, Kodama, and Tau Carbon. And WHS has been evaluated by several authors and organizations. For example, the National Academy report on nets in 2019 considered this a viable, relatively easy to implement pathway. And with the demo projects and research we have conducted, our assessment that the technology level is at 6 to 7 now. It does not involve truly unknown technology, but it does require putting together interdisciplinary science and practical knowledge. So the scientific basis can be viewed from the global carbon cycle point of view. And the terrestrial biosphere each year takes up 220 gigaton CO2. That is 6 times the current fossil fuel emission rate. And of course, most of that goes back right into the atmosphere by decomposition and respiration. So the natural carbon cycle is more or less in balance. So the concept is that if we can siphon off a fraction of this productivity and put it away into long-term storage, essentially transfer the carbon from the fast carbon cycle into the slow geological carbon cycle, we have the hope to sequester continuously a significant amount of CO2. So we're using the biosphere as a carbon pump, but then use wood as storage. So from the ecosystem level, this is really a carbon removal strategy and not really a carbon avoidance strategy, which is the case when you look at a smaller boundary of individual trees. So the global potential has been estimated to be between 2 to 10 gigaton, and using wood residuals will lead us to 1 to 2 gigaton per year. If we go for managed forests, we can get up to 10 gigaton per year. This number, 10 gigaton, is 5% of the terrestrial NPP. If you look at individual countries and regions, for example, in the US, the implementation can offset all the GHG emissions from its agriculture sector. And of course, the largest potential is in the tropics, where tropical rainforests are highly productive. So the method can be looked at from the 2 main aspects of it. One is wood sourcing, the other one is wood storage. So there are 2 ways of doing wood sourcing. Type A, wood residuals. This often has a lot of co-benefits. For example, utilizing the fire thinning wood and storm blow down recovery and urban wood residuals, forestry residue. And the counterfactual, of course, is important. For example, in the case of these wood residuals, probably be mulched or burned. So in that case, the comparison, the baseline is actually can be very well defined. When you move to managed forests, and as we say, this is where you actually can get a really large potential. And in this particular case, shown in this diagram, if you start from a marginal land or previously deforested land, you try to reforest it. And after the regrowth, where carbon sink saturates, you start to implement wood harvesting and storage. This can basically make that carbon sink continue forever. So it just keeps accumulating. The key, of course, is sustainability. We all know how challenging it is to ensure carbon forests are well managed. So MRV and governance is a key aspect if we ever want to go this route. So on the storage side, the engineered structure that is built to ensure the longevity of stored wood is, we call it wood vault. There are several versions people have envisioned. So in this illustration, I show a particular version that is to bury sustainably sourced wood, raw or minimally processed underground. A key is to take it below the active biosphere, which is often the top 1 meter or so, where decomposition, fungi and organisms and work on the organic material. So ensure that this is taken below that level, even though it's not that deep, but it's in a geological reservoir. So this condition, either anaerobic or in other versions, dry or cold, will ensure the longevity of the stored carbon. So the process is akin to the first step of a fossil fuel formation process. For example, you think how coal was formed in the past. And this, of course, is done by human engineering at an accelerated pace. So you can really think this as a reverse coal process. Now, the engineering details are very important. It's not as simple as dig a hole anywhere, it will work. So it requires digging trench and bury wood, cap with clay or other low permeability material. And then you can backfill the topsoil to ensure the original organic matter is mostly maintained. And the land on the top can actually be used for most purposes, such as grazing, cropland. You can even build solar farms and use as recreation and so on. So monitoring and maintenance are important. And one characteristic is because it's a well-defined physical system close to where we are. So if something wrong goes wrong in the future, it's actually reinforceable. And so here I give the example from the Montreal project where we bury 35 tons of wood. So start with trench digging, and then here trench is complete. And here you fill the wood that was piled on the side and down into the hole, and finally backfilling the topsoil. So the dimension of this particular trench was 20 by 8 by 5 meters, and the operation took 4 hours in March 2013. And we have excavated the samples about a year ago, analyzed the data, and it shows the convincing evidence that material buried below 1.2 meter is basically intact. Also, accidentally, we found this natural experiment, a 3,000-year-old red cedar log that was very, very well preserved. So we have identified anaerobic condition to be the key factor that enabled the long preservation, as well as our 9-year experiments preservation in this case. So here I want to show a process flow diagram that describes the Montreal project process. So you can see on the left is the photosynthesis and natural decay. That is outside the engineering boundary, which involves relatively straightforward process, wood collection, transport, and temporary stockpiling on the site. And then finally, the excavation burial. So the carbon emission in this case is about 2% of the sequestered carbon. And the cost for machine operation only is $29 per ton of CO2 buried. So finally, to summarize some of the key points here, wood burial is the first step of a fossilization process. Thus, it's a natural reversal of coal excavation and burning. And the durability, if done right, we think can be 1,000 years or longer, and it's distributed and highly scalable and relatively low cost and low capex. And on the MRV side, of course, it's very important. And but compared to some other methods, this is a closed system, very, in a way, we think it's relatively easy to monitor. And the land after wood vault is enclosed, and the soil settled can be used for many other purposes. And the footprint itself is already actually quite small compared to the carbon sequestered. Then the environmental impact, there are some, but we believe can be kept at minimum. And there are multiple co-benefits in many situations, such as waste management, fire risk reduction, extending carbon sink of reforestation. And sustainable wood sourcing is critical when we implement something like this at large scale. And we think it's already economically viable with the current carbon market and with megaton scale in coming years and gigaton scale in the 2030s. I guess that's all I have. Thank you.
All right. Thank you very much, Ning. So what I'd like to do now is proceed with a series of questions I'd like to explore with the panelists, and then we'll move on to the audience questions. Okay. All right. So first question for you, Ning. You indicate that ultimately this could potentially be scaled up to the gigaton level, right? Which is obviously the golden chalice in our field. What would that entail in terms of scale and logistics to move from relatively modest early start with this to 1, 2, 3 gigatons? What would that look like?
That's such not an easy question. That depends a lot on how how we actually do it. I can probably start with a couple of numbers. So on the wood sourcing side, to get 1 to 2 gigaton is non-trivial. And but the current world wood harvest is 4 gigaton CO2 equivalent per year. So 1 gigaton, and we're talking about 25% of the current wood harvesting rate. And this, of course, is not to say harvesting another 1 gigaton new, because I think this can be realized by just utilizing the wood residuals from the current operation. This is going to be, distributed really to look at where the wood residuals are distributed. Like in our area, the Washington, Baltimore metro area, there's actually a lot of urban forestry residues available. Then, like fire thinning, they are expecting a lot, like in the US West, Canada, and so on. So on the wood source side, it's really important actually to really get to the ground level, see the distribution availability of what these things are. But the top-down level view is, I think it's there. And then on the storage side, I guess the benchmark number we can use is in the US, there are 6,000 operation landfills. And from the engineering aspect, it bears quite a bit similarity from a landfill. So to sequester 1 gigaton CO2 equivalent wood vault, we estimate we can use about 1,000 landfill equivalent with each wood vault sequester 1 megaton per year. So 1 megaton times 1,000 of them is 1 gigaton. So of course, this is going to be distributed worldwide. It's not just the US. So it sounds like a lot, but when you distribute it out compared to the operations we run these days, I think it's doable. So I guess that's what I can imagine for now.
Okay. Marianne, you had something to add to that?
Yes, I could complement with a project that is registered with the Bureau Registry and Standard in Australia. And I think they reach 0.5 gigaton over 10 years. That's the plan. And of course, Australia is a large country, but they do need 300 hectares. And yeah, it is a large operation, but revegetating land that is currently quite bare, or this is already happening in quite large scale.
All right. Okay. Next question in this context. So obviously, when we talk about wood residue, there's a lot of potential uses, including in the CDR realm, right? Because alternatively be used for things such as biochar or BECCS. Why do you think this is the optimal approach from a standpoint, I guess, of carbon removal or co-benefits or both? I'll open that up to any of you.
Sure, I'm happy to jump in here and say a little bit about this. You know, I think Ning does a really important job at the beginning of kind of differentiating what the system boundary and what we need to consider when we're working with wood residuals is compared to managed forests. Thinking that the science and the accounting of that is still something that's really emerging, but we do have a very clear system boundary when we look at wood harvesting and storage of wood residuals. And two things that really come out of that is one, the relative amount of carbon that is stored for a relatively long period of time at a relatively low cost is the result of the wood harvesting and storage and wood vaulting process. And so, you know, I'll just to dive in on that just a little bit more, you know, the amount of carbon in the biomass that is ultimately moved into a durable product varies between biochar or bioenergy with CCS or wood vaulting. We think wood vaulting has a relatively high carbon storage efficiency, as high as some of the best BECCS options, but we think it has likely a longer durability than biochar applied to soils, which has also lower carbon conversion efficiencies. And so I think there's a lot of reasons why wood harvesting and storage and wood vaulting more broadly is this kind of this near-term opportunity in the biomass carbon removal and storage space. It's also, you know, the reason why we're seeing voluntary buyers stepping up and lots of commercial activity and, you know, several startups really trying to do this at the pilot and demonstration scale.
Yeah. Do you think ultimately, given the fact that BECCS, for example, also potentially gives you an energy source, right?
Mm-hmm.
If you're doing a full sort of life cycle assessment, does it still pencil out better than using wood residuals for BECCS, for example?
Yeah, it's hard to say. You know, it depends how you value energy and carbon, right? And what we need more of in the energy transition, right? Mm-hmm. And that's an open question. I think, you know, there are some kinds of BECCS that really allow you to capture 100% of the carbon and then make a valuable product, like electricity or hydrogen. You can also capture a lot of the carbon when you're making transportation fuels, but there's going to be this energy carbon trade-off that right. I don't know exactly where it will land.
Yeah, it's a fascinating question. One of many fascinating questions in our field, right? But thanks for that. That was really helpful. So
may I complement again with we already have quite a practical view of this topic in the sense that we are a standard and registry in operation. We have a handful of projects with this methodology, woody biomass burial or woody biomass storage in our registered projects. I think they are very much in different places where BECCS happens, where there are people and use for the energy. The woody biomass burial often happens in stranded places far off from communities that could benefit or use the energy. So I think that they are two very different types of opportunities, one in densely populated areas and the other one in these very far off outbacks often.
Can you tell me a bit more about it? Maybe introduce for those that don't know a lot about Puro your role, and then explain a bit of how you developed this methodology and maybe some of the challenges in doing it.
Thank you. Yes, happy to tell about Puro Earth. We are a standard and registry, quite young. But specialized in engineered carbon removals and only doing that for the past 4 years. We have currently 5 methodologies in that space. One of those is this woody biomass burial, as we call it. Then the others are BECCS and DACS, called the geologically stored carbon, biochar, and then 2 mineralization methodologies, enhanced rock weathering and carbonated materials. And by today we have issued some over 300,000 credits already to these methodologies or projects, and we are building new engineered removal methodologies in that space. I think the methodology development always happens when 2 things are in place. One is the science. There has to be scientific way to quantify how much carbon is stored, how long is it stored, what is the risk of re-emission. And then there needs to be projects that would use the methodology. So no sense in making a scientific methodology if there is nobody to implement it. So that's the sweet spot of doing it. And it's maybe a year ago when this methodology had enough science. Actually, the science part was quite good. It had already been captured up in IPCC, which is, I mean, taking peer-reviewed science and synthesizing it. So the science part was quite mature. And then there were these projects that were willing to start piloting and implementing these biomass storages. And what is specific there? So like Professor Zeng said, that it has quite nice benefits, large potential in volume in global scale, low cost, and then also this low risks. So it's not harmful to the environment or to the communities or people. And very often, so no co-harms or very few co-harms, but very good co-benefits through this kind of restoring landscape or clearing out problematic wood when it has been stranded or landed to wrong places. And then there are a couple of specifics that have to be taken into account. Of course, how is the biomass separated from the environment so that the decomposition does not happen, and especially keeping focus on methane, that everything is done to avoid that.
And is the MRV component of this difficult?
I think not especially difficult. There are much more complex things. So thinking of the net negativity, or how do you measure how much carbon is put to the storage and how does it stay there? Understanding how much carbon there is in wood is quite easy and sort of a common practice. So it's well known. And then this lignin, or these trunks and branches of wood do not decompose readily. So there is a small fraction that decomposes early on when it's put to the storage, and then it stops. And there is, like Ning explained, already starting to be field data that can be used to say how much of that happens in the early days before it reaches an asymptote. And then the other MRV aspects are similar as for any other methodology. The financial additionality or additionality in general is quite clear in this case. It does not happen on its own. It needs people and engineering to make it happen. And the environmental risks have to be covered, land ownership or right to use the land, having enough funds to do the closure and monitoring of the site after the burial or the storage. And yeah, these are more the legal or easement things that need to be checked during the project setup.
Okay, thank you. Okay, so one final question, and then we're going to move to the audience Q&A. I'll start with Dan. So obviously a critical consideration in this is durability, right? And Ning talked about the possibility of 1,000 years or more in this context. How confident do you think we are in terms of that durability of this of the wood vault process?
Yeah, well, I think the first thing to recognize here is that many of these are hypothesized and not tested at the scales to really have evidence that we're sure of. And so I see this evolving over time as we gain new information and as we do clear MRV associated with these projects. But I do think that there are a number of different proposed designs for wood harvesting and storage, and there are likely differentiated durabilities, I think, within the realms of scientific confidence right now. The process that Ning is describing, and specifically what was done with the Montreal process is the creation of an anoxic condition underground using a thick layer of clay.
Mm-hmm.
That's something we think that can really get up to, I hate saying over 1,000-year durability because very few things are sure after hundreds of years, but long-term approaching geologic scale durability. There's a lot we don't know about some of the other approaches that have been proposed, including burial in dry places without kind of similar lining or necessarily anoxic conditions. I think above ground wood storage is another place where I think there's really not great practice or evidence of 1,000-year type durability. It's probably going to approach closer to 100 years, something more like biochar because it's something that's in the built environment. So I think that's where some of that stands. I think we can narrow those bands over time by doing clear and consistent MRV. And this ties into how we use buffer pools and how we really improve the practice of wood vaulting as the science evolves.
Okay, thanks for that. Anything to add, Ning?
Yeah, in principle, really, I think what Dan really said it well. It's not like calling it a wood vault or bury it will all have the same durability. It really depends on how you do it. If you look at the archaeological and geological evidence, there are those long duration, hundreds of thousands of years to millions of years of examples of well-preserved wood, but you also have ancient shape and so on that's gone.
Right.
So the science is there actually, but it's interdisciplinary. And I think in terms of moving to the next step, as Dan was describing, how do we know under what condition what the durability is? That would be really like a key research question. I think by pulling together different communities, we can already have a very good definition, a guidance, for practice. And then as these current projects go on with monitor and verification put in place, then we will be able to actually move to that stage, Dan invasion, where we can assign durability given a particular way of building a wood vault.
All right, thanks for that. Marianne, did you have something to add there? Oops.
Hearing you.
Oh, now I can hear you.
Okay, maybe there was a kind of sorry if I talked over somebody.
Didn't.
No, okay.
Go ahead.
I wanted to comment about that. In our methodology working group, there were people who had as their job to try to decompose wood and other biomass residues, making methane or biogas, and really trying to make that side of things happen. And they said that it is difficult. It's easier to preserve and keep it stored than try to make it to form methane and turn to biogas. So I think that then controlling the conditions where when you really engineer it for trying to preserve it, I think that really is a phenomenon that is there, whether it's 100 years or 1,000 years. I think in the current climate crisis and the budget that we have left, 100 years is good. If it's more, that's better. But let's start with the 100 years.
Okay. All right. So in the questions, we have an array of technical and commercial queries. So let's move to some of those. First question, to attract outside investment that will be needed to scale this approach, do you have confidence that Woodvault's approach to carbon capture is patentable subject material and thus capable of being more easily commercialized? Maybe start with Ning on that.
Okay. So that question, if the key point there is whether it's patentable, I'm not a patent lawyer. I actually don't know. I would think, the general concept, it's fairly understandable. I would say it's not patentable, but specific engineering techniques, follow on previous question, how to ensure the durability, I think very likely, that different techniques could be patentable. I don't know if that's the key point of that question or some other.
Yeah, I mean, I don't want to put words in the questioner's mouth, but I think the essence of it is if you're going to commercialize this, right, and create a carbon niche, you're going to need unique aspects, right, that others cannot easily replicate, right?
Yeah.
Okay. Either one of you want to add anything to that, Dan or Marianne? Okay.
Maybe from another perspective, I think it does have a very many natural phenomena that cannot be patented. Maybe some monitoring or other aspects could be, but we have seen it being commercialized. Actually, an insurance company has done advanced market commitment to project. So commercializing does not necessarily need patents. You just need to make it more cost efficiently than others, and then you win the game.
Okay. All right. Next question says, I understand the idea that the carbon cycle effects of a permanent carbon pump approach could be self-sustaining, but how should we think about the possibility of nutrient depletion? Does that issue look similar to or different than the way it applies to commercial timberland management? Maybe start with Dan on that.
Happy to venture.
Oh, Dan, you froze up.
Sure.
Oh, Dan, you were frozen for a moment. Maybe start again.
Okay, happy to. My apologies. I do think that nutrient retention and alteration of global nutrient flows at scale is one of these really large scale kind of governance questions that hasn't been resolved in the case of wood harvesting and storage. Now, at this case, I mean, we're talking about sizable impacts in terms of comparing nutrient export of nitrogen in particular You know, on the order of a portion of kind of current global flows when you're doing this at the gigaton scale. I think maybe 10 gigatons would be a quarter of global nitrogen flows, but sorry, I don't have the exact stat on hand. So that is, you know, but 10 gigatons is a very, very large amount of wood harvesting and storage. You know, it scales linearly to the scale of the industry. You know, I think other aspects of nutrient management, like making sure you're taking browns and not greens, as in you're taking the actual low nitrogen part of the wood rather than the high nitrogen part of the wood, is a really important on the ground implementation question here. So I think, you know, this is one of those things that you know, I think evidence will emerge over time, and really societally mediated. There will be a decision made about the appropriate scale of this approach compared to other, perhaps more nutrient efficient forms of biomass carbon removal.
Okay, Ning or Marianne, anything? Ning?
Yes. In fact, that's a very important question. And, you know, being a carbon cycle scientist, that's, you know, very critical aspect of doing things, you know, at such a large scale to consider. But I want to give us some specific numbers just in terms to quantify the, you know, potential order of magnitude of this potential nutrient loss. One important reason we say woody biomass, but not leaves, is exactly because to minimize nutrient loss. Wood is actually nutrient poor, has 10 to 20 times less nutrient compared to leaves. It's a structural material, mostly just CH and O. So the natural nitrogen deposition, as well as anthropogenic nitrogen deposition, is 10 to 100 times larger than this 10 gigaton rate, if you translate into nitrogen in it. So at a global scale, we actually know pretty well this will not cause a significant nutrient loss, burying 10 gigaton wood. However, it is a local problem. So when you manage a piece of land, so you will going to have to look at that piece of forest. On this aspect, the forest industry actually has a lot of experience, and some of the intensely managed forests in, for example, southeastern US, they actually do fertilize a little bit every some decades. And so the point is that one can start doing it if, well, with good monitor and process in place. If we find nutrient depletion becomes a problem, we can slow down the process or stop it altogether, or fertilizer, yeah, whichever, you know, has the most best, you know, outcome. So it's a issue that is important, but I think it's manageable.
Marianne, is that part of the MRV methodology currently that Puro is using?
Yes, in the sense that it needs to be the trunks and branches, not the leaves and needles. They carry the nutrients, just like said here, but also they are the parts that would decompose and create methane and all the bad things in the storage. So they shall not enter the storage.
Okay. Okay, next question. What is the minimum depth required for wood burial to be effective on the 1,000+ year range? And the sub-question is, how does this minimum depth change with soil composition, such as clay-heavy soils?
Yes, it depends on very much on the permeability. If you have sandy soil, air can freely go in. You can have 10 meters of sandy soil on top. It's probably not going to work well. And so if you have good low permeability clay soil, and also based on experience with landfilling pits, and our Montreal project data actually provides a very strong quantitative suggestion here. The ancient wood was just 2 meters below the surface. And that place is clay in situ. So just all, you know, all clay soil. And there's a topsoil that is about 1 meter or so, which allows roots to go down. So you discount that, there's still 1 meter of low permeability clay. So we are proposing on that order, 1 meter or more low permeability clay, and would be sufficient to get you to hundreds years of time scale or longer.
Okay. Anything else to add there?
I'll add, I think 2 other design considerations is you have to understand the local water table. And I think a big wild card here, of course, the unanswerable question of termites, you know, an organism we barely understand, and it's subterranean patterns. But I think this is why MRV is going to be really helpful in the short term.
Yeah, I could complement that these many of these risks are actually dealt with beforehand by site selection, and there are these topology, hydrology, salt. I mean, it can be so the area do not go to areas with the termite risk. So a lot of these things are dealt with by right selection of the source of biomass and site to do the storage in.
Okay. All right, so we have another site question. If you're calculating potential based on global NPP, you're implicitly assuming that all the world's forests, including the very large tropical forests of the Amazon and Congo basins, have become accessible to the machinery needed to construct wood vaults. But access, specifically by road building, has been shown to be one of the key drivers of tropical deforestation. Have you included the additional deforestation due to roads in your, I guess, in your life cycle assessment calculations?
So in our 10 gigaton estimate, we're not talking about uniformly, you know, take out a certain fraction, 5%. The 2013 paper by this scientific consortium actually described the detail how we did this estimate. Basically, conservation lands are set aside, no touch, and that's 50% for the tropics, 20% for mid-latitude. And you would be surprising, naturally, maybe surprising for you to know that most of the world forests are actually within 10 miles of road access already. And of course, you have pristine Amazon forests and so on there. So those conservation forests, we definitely don't want to touch. At least personally, I think we should not. And so that 5% will come from more intensely managed area or already managed area with wood residuals.
Yeah, I think wood residuals is really an intervention into the decomposition aspect of global global net primary productivity. I think is the best way to think about it. Of course, as you move into managed forests, if you're growing a forest and managing it for the purpose of burying the wood, we need to absolutely think about those kinds of those knock-on effects from a carbon perspective, but also from a forest sustainability perspective.
Yeah. Do you ever contemplate, Ning, that we would reach that point where we would also incorporate a managed forest element?
Actually, by talking to people in forestry, that is very, very actually possible. And especially when the timber industry is in distress, when the market is slow. And there are a lot of crappy wood that cannot be used for timber. You know, furniture market is limited. And even with the currently managed forests, there are a lot of them are not really utilized. The landowners, like in southern US, many of them can barely make a living to maintain their generations of forest land. They would like to make enough profit so that they can live on that land and maintain that forest. I think in places like this, sustainably manage it for this additional carbon value actually already has, I think, has quite a, you would be surprised. There is a community who can support this if the market and governance, is in place.
Okay, thanks.
What we have seen in practice where we see it starts is not these forests that grow wood for other purposes. It's the stranded land or stranded biomass that where we have seen that the first projects come online. So not the typical forest management, but something which needs revegetation or otherwise is already slash piled or flooding a river that needs to be cleared out and then done something with it when it's in a very far off place and nobody needs it and it's not economical to transport it for any use.
Okay, thanks. All right, next question. How was the decomposition rate from microbial and insects extrapolated from about a 1-year experiment to a 1,000-year time frame?
That's a great scientific question. And we have a 9-year experiment. So, of course, the uncertainty, when you extrapolate from 10 years to 1,000 years by 2 orders of magnitude, any small error becomes so large that that central value could fall even on the other side. So we can't really, just based on that mathematical extrapolation alone. But the good news is experiment tells us the process. If I may dive into a little bit detail here. So when you look at the wood, it's mostly lignin and cellulose. So with lignin, which is not digestible by anaerobic bacteria, protecting cellulose. And so this part is 90% or more of the total fresh wood biomass. So with this holocellulose and the lignin structure, really pretty much nothing can attack it in anaerobic condition. Termites and fungi, they need oxygen. So the small amount of anaerobic bacteria, they can't really tackle the lignocellulose structure. So to me, the long time durability really comes from these archaeological and geological evidence. There are some very nice studies on archaeological wood and geological wood. Just our own experiment, that natural experiment from Montreal, we know precisely what the condition is, how it was buried in this river valley, how long it has been. And we can see the structure well preserved under electron microscope. And we understand the permeability. So we use this kind of evidence that adds to our confidence in terms of process understanding to say, yes, if you do it right, we can get to hundreds to thousands of years. And of course, definitely need more research. I would love to see more research on this.
Okay. All right. Next question. What are the land use requirements for sequestration of a gig of CO2?
I guess the question is about the storage space, right?
Yeah.
Yeah. So what do we call one wood vault unit occupies 1 hectare. So the size of 2 football fields. And we said that 10,000 of it, 10,000 hectare, basically would accommodate 1 gigaton. 10,000 hectare, that is 10 kilometer by 10 kilometer. If I'm fast enough, correct me if anybody say my math wrong. So 10 kilometer by 10 kilometer area for 1 gigaton. If you stack these wood vaults on top of each other, so you could be even more space efficient. In other direction, when you do smaller wood vaults, it may may occupy more land space.
Just to put that in perspective, I mean, we're talking about hundreds of millions of hectares of land in agriculture or forestry around the world.
Okay.
And of course, if we're using managed forest, there's another part of that land footprint. But, yeah.
Okay. All right. Next question. What are your thoughts about the ability to get other feedstocks qualified that don't meet the definition of woody biomass, such as switchgrass, bamboo, fast-growing trees, leaves, etc.? Trees are not readily available in the Midwest.
Maybe I can start from our methodology. There is always a core and key fundamental phenomenon that our engineered carbon removal methodologies are based on. And here in this woody biomass storage, it is the lignin containing biomass source put into an anaerobic or separated from the atmosphere. In this case, other than woody biomass would not be eligible in this methodology. So the other stuff behaves differently, and then it can't be monitored and reported and sequestered in the same way.
Okay.
I would agree there. I think there's really the unique structure of wood with the lignin for recalcitrance is important. Of course, there are other kinds of lignocellulose, but we're really talking about coarse wood debris and larger for the purposes of preventing decomposition.
Okay. All right, we have time for one more question, I believe. And question is, do we know what the soil organic carbon was in the topsoil that was disturbed to bury wood in the Montreal example? Was the potential carbon loss from topsoil accounted for? So obviously that'd be for you, Ning.
Yeah, I actually don't remember if the Puro methodology includes that, but if I would do advise anybody to do it, I would definitely carefully measure the carbon in that topsoil. And then after you refill it on top, and you probably lose some because it's disturbed, then look at the process, ideally probably model it with some data points to validate. And the good news is soil carbon does recover. So after some years of regrowth, depending on what you do on the top, so we can expect much of that CO2 carbon to come back. And so if you do full carbon accounting, you do want to take into account of that.
Marianne, anything to add in that context?
Yeah, we do advise to estimate all emissions which are deducted from the gross storage. The places where we see these first projects are very poor in topsoil, so the carbon is already almost gone, and that's why the revegetation is needed. So, but yes, that is estimated and deducted, and remembering again that the actual storage pit is quite small area, like 10 by 10 meters, to store quite a large number of biomass. So not a lot of topsoil is disturbed compared to the size of the operation.
Okay, thanks on that. Okay, I lied. I think we have time for one more question here. Based on the experts' knowledge of the CDR approach, roughly how many companies are active in this space? Maybe Marianne might know that?
Yeah, and I would advise everybody to keep an eye on registry.puro.earth and visit our webpage, puro.earth. But at the moment, I think we have a handful of registered companies, and then another 10 or more in active discussions in the funnel. So that's my understanding of where the situation is. So please, there is room for more for this very positive and potential low cost, low environmental risk sequestration method.
Do you know if that other crediting organizations such as Vera are also developing methodologies in this context, or have, Marianne?
I have not heard that. At least when we entered this came out with this methodology a year ago, I was not aware that somebody else was active.
Yeah, that's your understanding too, Ning? Is there any other crediting organization that's either developed one of these or working on a methodology?
I don't have any additional information.
Okay. All right. We have reached the top of the hour. This was fascinating. I really want to thank Ning and Marianne and Dan for joining us and explaining this process, and excellent audience questions as usual. We will be back in a couple of weeks. We'll publicize in the same venues that we always use. I hope you'll join us again. And once again, thank you, everyone. Goodbye now.
Thanks for having us.